Number 8, pretty easy question. We're just looking to run through the process that we were doing earlier with regard to graphing. You guys remember doing these worksheets here. And I'm not asking you to graph on this. I just want to get the information that would be pertinent. And so again, we run through the idea. Critical points are going to come from our zeros and our restrictions. So we want to look at this numerator and we want to see if we can break it down. As I look at this problem, I recognize that if I AC it, this is a perfect square up here, the only way that 2 is going to come from 1 is with 1 and 1. So I can break this down as x plus 1 over, the denominator is already broken down, so it's x minus 3. And so to answer the questions, the zeros can be found by figuring out what would make a 0 in the numerator. If I plug -1 in, I would get a 0. If I plug -1 in, I would get a 0. So we would say at x equal -1, you get your zeros. Vertical asymptotes come from any restricted value in the bottom, or any 0 from the bottom. So you have vertical asymptotes when x equals 3. So you say you don't want x to be 3. X cannot be 3. That produces a 0 down there. And then for this one, it does talk about a slant asymptote. And we might as well talk about the slant asymptote. Slant asymptotes would come from the ratio of leading terms is the way I usually teach this. If this is going to be x squared to x squared, you would say it's a horizontal at y equal 1. Well, this isn't x squared to x squared. This is x over 1, which for just a general purpose idea, you would say, oh, that's going to be y equal x. But the question is asking for the specific slant asymptote. And so now we actually want to see a little bit more work. And the way you do that is just traditional division of polynomials. You'll say x squared plus 2x plus 1, and you want to divide by x minus 3. I know when I used to teach this in Algebra 1, the kids would go crazy over this. It's just traditional division. If you know how to divide, you can divide a polynomial. So the question is, what times x produces x squared? X. And so then you multiply through on both parts. So x times x is x squared. X times -3 is -3x. And just like you do in traditional division, you put a line and you change the signs so that you could subtract these out. So when I change the signs, this would go to -x squared and plus 3x. The first term drops out. This becomes 5x, because 2x plus 3x is 5x. Bring the next number down, plus 1. And you start all over. And so you say, what times x produces 5x? Well, positive 5 would do that. So 5 times x is 5x. 5 times -3 is -15. You put a line and you want to change those signs. So you're going to say -5, positive 15. This drops out and it leaves you with 16. Nothing times x would give you 16. So this is like your remainder. And since nothing times x gives you 16, you're going to say plus, and you just turn this into a fraction, 16 over x minus 3. Now the value of doing traditional division like this is that when you talk about the slant asymptote, you talk about end behavior. If you put very large numbers in here, if I put -500 in there, for all intents and purposes, this drops out. If I put positive 500 in there, 500 minus 3 is 497, so 16 divided by 497, very small number. So for all intents and purposes, this drops out. And so you get this slant asymptote of y equals x plus 5. And so if you were, pardon me, if you were at -500 or positive 500 for the x value, for all intents and purposes, if you looked up and saw this graph, it would look like an x plus 5. And that goes back to, it almost reinforces what I'm saying here. The ratio here is going to be x over 1. You know it's going to look like an x, a y equal x. It just happens to be shifted up 5 units. So that's your slant asymptote. And then the last thing I ask you to do is a sign check. Sign checks have nothing to do with your slant asymptotes. So you only look at your zeros and your verticals. In this case, I put a -1 in here. I put a 3 in here. I know at -1 I'm 0. At 3, I'm a DNE. and you're just going to plug some values in to see what happens. And so we can do that. It's pretty easy. I'm going to choose a number over here in this region. So let's try negative 10. That would produce a negative, and a negative. So you're going to be beneath the x-axis there. Between negative 1 and 3, obvious choice to throw in there would be a 0. So that would be positive, positive, negative, which means you'll be negative there. And that kind of makes sense because you have the double root here. It makes sense that it's going to come up and go back down. And then over here, let's throw a very positive value in there, like 20. This would be positive, positive, positive. And just so we can show what we're talking about here, let me plug this into my graphing calculator. I've got x squared plus 2x plus 1, put parentheses around your numerator, divided by x minus 3, just like that. And then I'm going to graph it, and we'll see what it's doing. Hopefully we get to that point where you guys become comfortable enough where you can start predicting what these things would look like. So when I'm looking at this, it's telling me I'm beneath the x-axis. You see how I'm beneath the x-axis? It goes to negative 1, hits that 0, and then it stays negative. Well, since it stays negative, it has to go back down towards that asymptote, and that's what you see here. I think we had an example earlier where we didn't see the second tail. The second tail has to do this. It has to go like that when we're looking at this graph. It has to follow that slant asymptote of y equal x plus 5. So it's going to go from a vertical asymptote, come down and then go back up because it has to follow this y equal x plus 5 idea. So if I zoom out enough, what I will see is this part of the graph show up. It won't show up on my grid because I have a standard grid on there right now. And so that's essentially all you have to do for number 8. I'm going to skip 9 because it's pretty much the same idea. We're just dividing that thing out. The only difference would be that when you do the numerator, you are going to want to use that polynomial root finder to figure out what your zeros are. And so I'm going to kind of let that one just go for you. And then I think that would be good enough for you to be able to get through that take-home test.